afternoon and welcome to our lesson today. We are still on waves and we have been looking at properties of waves where we went as far as interference, and we agreed that interference is actually the merging of two waves to produce a resultant wave. Now, the two, we called them components, and we gave the final wave the name resultant wave. Now, we were able to look at a few conditions that will favor the interference of our waves. For example, we said that the component waves have to come from coherent sources. Remember that interference is just between two waves, and they have to come from coherent sources, where coherent means that the sources are narrow, they are close to each other, and they are actually parallel. Now, depending on the angle through which they meet, as well as their amplitude, and bearing in mind that the amplitude is actually vector quantity, we said that the resultant wave should have an amplitude A, which is capital A, which is actually a vector quantity of the component amplitudes. Now, we were able to look at interference of transverse waves, and we appreciated the three results that we should expect from each of those particular the two waves that actually interfere. We appreciated the three situations that we can have as our result. Now, we want to see whether waves, the sound waves, can actually interfere, because sometimes you are working in your room, you have some two speakers, for example, situated at different corners of your room, and as you walk along the room, you will realize that sometimes the sound is actually exaggerated, sometimes it's soft. Now, we want to find out why should a sound behave like that. In that case, we are going to look at two speakers, which we are going to call A and B. We are going to connect them to the two speakers to an audio frequency generator. We are going to connect the two speakers to an audio frequency generator so that we have something like this. We connect them to an audio frequency generator. Let us note that the speakers have to be of the same size. There you go. We have a point O at the middle, and we want to let our speakers be at equidistance from our audio frequency generator. our audio frequency generator is going to work as the source of disturbance. Now, remember we said that a wave is actually a transfer of energy in form of disturbance. Now, we will expect that if you were to walk along a line XY in the room where the speakers are, so that this one is loudspeaker A, this one is loudspeaker A, the other one is loudspeaker B, you will expect to have to experience alternate soft and loud sound along the line XY, that you're going to have alternate soft and loud sounds along that line. Now, there is one point here where we have an equal distance from the generator to loudspeaker B as well as to loudspeaker A. That is our point of reference, and we are going to call it D. From there, you will experience a soft sound. Again, you will have another loud sound, a soft one, and again you will have a loud sound. Again here you will have a soft sound, a point of loud sound, and alternating with soft sound. Now, what is happening is that areas of loud sound are areas of constructive interference. These areas where we are having continuous sound, which is loud, is actually an area of constructive interference, while these other areas are areas of destructive interference. They are areas of destructive interference. Now, OD, if you were to walk through OD, you will have loud sound throughout, loud sound throughout, because that line is always equidistant from the two speakers. Now, for us to have successful interference patterns here, we have made sure that the two speakers are actually equal in size, and they are connected to the same source of disturbance, which we are going to call our audio frequency generator. Now, what happens is that our speakers act as coherent sources. They act as coherent sources. From the diagram, we can be able to attest that they are actually equal, close together, and parallel, and therefore they qualify to be coherent sources of sound, and therefore the waves that will emanate from the speakers, the waves that we are going to generate from this particular setup, are going to have equal frequency. They are going to have equal wavelength, and they are going to have equal speed. The three conditions will favor the process of interference of the two, resulting to the interference patterns, which we are going to experience as patterns of constructive and destructive interference, which are going to be actually demonstrated through the soft and loud sound. We could also consider light waves, interference of light waves, and see what we can say about the same. And here we are going to use a source of light we are going to call monochromatic. A source of light that is monochromatic is a light that is only in one color. Now, we agreed that light as a wave has different colors, but you can make it to have only one color, and that is what we call monochromatic light. Now, here we are going to incorporate different processes where we are going to pass the monochromatic light through a slit we are going to call S1. This slit diffracts. It diffracts light, wavefronts of light, so that now we can have some circular wavefronts. Now, these wavefronts, we again pass them through another pair of slits. Remember that the direction of travel of the waves is from left to right. So we are having the diffracted wavefronts turning into a circular pattern. Now, again, we come to a pair of slits which we are going to call S2 and S3, and here we expect light to be further diffracted so that we have circular wavefronts from S1. We also have some circular wavefronts from S3, assuming the same pattern as the incident. Again, we are going to maintain the other characteristics of the waves. Now, again, the new wavefronts are also moving in the direction of the first wave, so that now direction is maintained. Direction is maintained, as well as wavelength and frequency. Now, what happens? Our source of light, which is monochromatic in nature, is going to be passed through S1. If this one this source of light was multichromatic, meaning having many colors, we expect after diffraction we will have some patterns depending on the wavelength of different colors. But now here, now that we only have one color, when we diffract it, we are going to have clear patterns of diffracted wavefronts. Now, these wavefronts will act as incident to S2 and S3. So this diffracted wavefront is what is going to illuminate S2 and S3. And after passing through the slits, we expect that the light is going to be further diffracted so that we have two patterns or two waves emanating from the same, and the two are the ones we expect to interfere so that we can have some patterns. Now, if you placed a screen somewhere there, so that now the center of your screen is equidistant from S1 and S2, we are going to experience the first bright fringe. Now, there will be a second fringe here at a point. So here, where we have the first bright fringe, S2, let us call this one point O, S2O minus S1O is equal to 0. Or if you may, you can say S2O is equal to S3O. That S2 to O will be equal to, this is the distance that we are talking about, so that the point O is equidistant from S2 and S3, and the result is a point of, it's a point of constructive interference, which we are going to call a bright fringe. Now, that bright fringe is going to be followed by a dark fringe, and this one occurs where S2, let us call this point R, minus S3R gives us one wavelength. Therefore, these two sources are actually coherent sources. We have made them close to each other. They are narrow and parallel. That's why we claim that the two are actually coherent. Now, the first bright fringe was formed where S2O was equal to S3O. Now, the second one, we are claiming that the point S2R minus S3R is going to give lambda. Lambda is one wavelength. Lambda is actually one wavelength. Now, we could have another one. where we could have another one. Sorry. The upper part will have S3 as the bigger. So S3R minus S2R is what is going to give you lambda over 2, which is half a wavelength. Half a wavelength. Now we can have another point P, where now we have the second bright fringe, and that is where S3P minus S2P will give us a whole wavelength. S3P minus S2P is giving us a whole wavelength. Another constructive interference giving us a bright fringe. And note that dark fringe means destructive interference. A destructive interference. Now, clearly, we are going to have alternate bright and dark fringe depending on the location of the point you are considering along XY. Along XY, if XY was to be your screen. Now, there are some things that we need to note here is that the dark fringe will be formed where we have now the first dark fringe is formed where lambda over 2, here is lambda, then we have 3 over 2 lambda, then we have twice the wavelength, and the pattern continues. Therefore, constructive interference occurs where we have the path difference. The path difference from the first and the second slit is a multiple, whole number multiple of lambda. That is a whole number multiple of lambda. However, the dark fringes form dark fringe forms where path difference is half multiple of lambda. A half multiple of lambda. Now the whole of that process is called the Young's double-slit. Young's double-slit experiment. The Young's double-slit experiment is what we use to demonstrate the interference patterns of light waves. I want to repeat the process that we have monochromatic light so that when it is diffracted, it does not form different patterns depending on wavelength of different colors. That is why we insist that the source of light should actually be monochromatic. Now, that light is passed through a slit and is diffracted so that it forms some circular pattern, which in turn acts as the source of light for S2 and S3 along its path, where it will be further diffracted so that it can form some two distinct patterns of diffracted light. Now, these two are the two waves that we expect are going to interfere constructively at some point, yielding some bright fringes, and destructively at other points where we shall have dark fringe. We said there will be a central point or equidistant from S2 and S3, which are our two coherent sources of light, and that is where we expect the path difference between the two to be 0. And therefore, if the path difference from S2O and S3O is actually a 0, we are going to form the central bright fringe. Now, there will come another point where you subtract the S2R minus S3R minus S2R, you will have a half multiple of lambda. That is the point where we expect destructive interference to take place, and it will yield the first dark fringe. Now, it will be followed by another region where the path difference will be a whole number multiple of lambda, and those are the areas we expect to have our bright fringes. Now, that one will form a series of bright and dark fringes representing constructive and destructive interference respectively. Now, we have some points to note. We have some points to note about our sources S1 and S2. They must be coherent. And by coherency, we mean parallel, close, and narrow. Again, we looked at the condition necessary for the formation of realistic diffraction patterns, and we said that the slit has to be as narrow as possible. Now, interference is only exhibited by waves that are interference is only exhibited is F. It is actually a property of progressive waves. Is actually a property of progressive waves. And a progressive wave is one that moves continuously from the source. Moves continuously. It moves continuously from the source. Moves continuously from the source. And that way, we yield some properties which are necessary for two waves to interfere. We said that for two waves to interfere, they have actually to be equal. And by equal, we mean they are progressive, they have some wavelength, they have some speed, which is almost equal to each other's speed. Now, there are times when we shall not be in need of any wave as a result of interference. That way, we can allow some two waves to interfere, but these waves have, they are actually equal. Now, we want to look at interference of waves, which yields a stationary wave. Stationary wave. A stationary wave. Now, what is a stationary wave? We agreed that wave is transfer of energy in form of disturbance. Then why should we say that a wave should be stationary? Or rather, when can we say we've formed a stationary wave? Now, this one is a wave formed when two equal waves traveling in different directions superimpose on each other to form a wave with zero amplitude. We have waves which are equal but traveling in different directions or the opposite directions. Now these waves superimpose on each other, or they interfere to form a wave with zero amplitude. That way we shall claim to have formed a stationary wave. Let us take a diagram. We have two waves. Let us call this one wave 1. Then wave 1 has an amplitude A1. Then we want it to superimpose itself on another wave which has an amplitude A2, and let us note that A1 is equal to negative of A2. Now that way we are going to have the amplitudes. You see, we said that for the two waves to interfere, their amplitude is the vector sum of individual amplitudes. Therefore, we expect that the amplitude of the resultant wave will be A1 plus A2. And we said that A1 and A2 are equal but opposite. Therefore, we can say that the resultant wavelength, the resultant amplitude will be A1 plus negative A1. In this case, where negative A1 represents our A2, or you could call it A2 plus negative of A2. Why are we claiming such a situation? Because we have said A1 is equal to negative A2. Now when that happens, we are going to form a wave which is having an amplitude that is 0. Because if you add a number and a negative of itself, it is going to form a 0. Therefore, we are going to have a resultant wave with 0 amplitude. So here we have these two as the component. These are the component waves, and this one is the resultant wave. We have the component waves and the resultant waves. When that happens, now we have what we call a stationary wave. Now, clearly, if we could draw the waves and remove the axis so that we have something like that. We have another component wave. We have a transverse wave. Then we have another component wave. That's the first component wave. Then we have another one. So that now they interfere to form as a stationary wave as shown. Clearly, we have some points where the wave has 0 amplitude. 0 amplitude. These are regions that we call the nodes. The nodes. Now, the particles at the nodes are having 0 displacement. However, our wave here at other points has maximum amplitude, meaning maximum displacement. And these areas, we call them antinodes. So we have nodes and then we have antinodes. We have said that we have had 2 waves interfere, so that now we formed some parts of 0 displacement as well as other parts where we have maximum displacement. Now, areas of maximum displacement, are what we call the antinodes, or A. And areas of 0 displacement, are what we call the nodes, or we could call them N. Those are areas of 0 displacement. Now, Clearly, you can see that from a node to another, the distance between a node and another one, successive ones, is what we call lambda over 2, and is also equal to distance between an antinode and a successive one. That we have those distances as half of lambda. Therefore, it is also worth noting that between a node and the immediate antinode, the distance is actually lambda over 4. Those are important aspects to note when it comes to stationary waves, because they will inform our characteristics of stationary waves. But before we go to characteristics of stationary waves, we can look at conditions. We can look at conditions. We can look at conditions necessary for the formation of stationary waves. We can look at conditions necessary for the formation of stationary waves. We have already said that stationary waves are being formed by two waves which are superimposing on each other, and the waves are actually equal. And why should we say that the waves should be equal? They should actually be equal so that when the amplitudes are added together, they are going to cancel each other. Because these two waves have the same amplitude but traveling in different directions. Therefore, when you look at the vector sum of the amplitude, it should actually give you a 0. Therefore, we could say that for two waves having the same amplitude, for two waves having the same traveling in different directions, to form stationary waves. For them to form a stationary wave, they should have, for them to actually form a stationary wave, they should have the same speed. They should have the same speed. They should have the same frequency. And they should have the same amplitude. They should have the same speed, the same frequency, and the same amplitude. Now, for two waves to be equal, they should have their speed, their frequency, and their amplitude equal. However, being a vector quantity, the difference in direction negates one from another. The difference in direction, note that a wave is actually a vector. It's a vector quantity. Therefore, direction in itself becomes a very important aspect when it comes to comparing the sizes of the waves. Note that vectors that are equal have the same magnitude and they travel in the same direction. But here are two waves with all the characteristics that we are looking for equal, but the direction is actually different, and this one changes the whole equation. Now, if you achieve those conditions, you are sure to make a stationary wave. Now, there are some differences that exist, or we can first look at properties of stationary waves. Properties of stationary waves. Properties of stationary waves. And we start with the obvious. Number one, it is formed when two equal and opposite waves interfere. They are formed when two equal opposite waves interfere. It is characterized by nodes at points of zero displacement and antinodes at points of maximum displacement. At points of maximum displacement. We have already seen that where we have seen that when the two waves interfere, we are going to form a series of nodes and antinodes where the antinodes are going to be at points of maximum amplitude and the nodes are going to be at points of zero displacement. That is what we mean by that. Now, number three, between two nodes, particles between two nodes, particles have different vibration frequency. Particles have different vibration frequency between two notes. That is the third characteristic. And then the final one, vibration of particles at successive antinodes is in phase. That the vibration of particles at antinodes is actually in phase. In phase, we said that for two waves to be in phase, they have to be moving in the same direction at the same level of displacement. That is why we say these particles are vibrating in a manner that they are moving in the same direction and at the same level of displacement on the wave. That is what we mean by particles being in phase. We could add one more. We could add one more characteristic, and the distance between two nodes, that is the successive ones, or antinodes, let us use or antinodes, is actually have a wavelength, while distance between a node and an antinode is actually lambda over 4. Quarter of a wavelength is actually a quarter of a wavelength. Is actually a quarter of a wavelength. Now, a good example of a formation of a stationary wave is when you fix one end of a musical instrument. Let us call this one fixed end of a musical instrument. That's a fixed end of a musical instrument. Then from another one end, let us say, for example, this musical instrument makes its sound by way of vibration of a string. Now, you pluck a string to an end. You pluck a string at one end, thus producing a disturbance. Here, you pluck a string and you produce a disturbance that is actually going to be carried out as a wave. Now, what happens when you get to the other fixed end? It is actually going to behave like a reflector, so that now your wave is going to be reflected back you have your first wave, which was created through sending a disturbance through the string. Now, when it is reflected, you form an equal opposite. You form an equal opposite wave, which we are going to call the reflected wave. So this one is the incident wave. This is the reflected wave. Now what will happen is that the incident wave is going to superimpose itself on the reflected wave, and the result will be a stationary wave. A stationary wave. The stationary wave is going to have nodes at those points. We have the nodes. Then we have the antinodes at the points of maximum displacement as shown in our diagram. And that way we can claim to have successfully generated a stationary wave. Now at these points where we have the nodes, the antinodes, that's where we are saying that the particles are actually vibrating in phase. However, at nodes, the particles are actually stationary. The particles are actually stationary. Let's look at the differences that exist between progressive and stationary. Progressive and stationary waves. And here we are going to tabulate them so that on one side we have the stationary and on the other side we have the progressive. Now we have discussed the two. We need to find out how different are they from each other. Now, the first one is the distances. Distance between two nodes or two antinodes is actually half a wavelength, and here distance between crests or troughs is actually equal to a whole wavelength. Now, number two is that stationary waves do not move. They do not move, and therefore energy is not transferred. It's not transferred to a point away from the source. To a point away from the source. How about progressive waves? Progressive, even from the name, it suggests that they are actually in motion. Therefore, they move and transfer energy. And they transfer energy from the source. They move and they actually transfer energy from the source. We could also say something about amplitudes. amplitudes of particles. Amplitude of particles between successive nodes is different. The amplitude of particles between successive nodes is actually different. How about the progressive? Amplitudes of particles that are in phase, is actually the same. For progressive waves, so long as particles are in phase, you expect their amplitudes to be equal, but that is not the case with amplitudes of particles on areas where we have nodes which are successive. On a stationary wave, we expect them to have different amplitudes. Now, the final one, vibrations of particles between successive nodes are in phase. Again, I will remind you that if we say that something, if we talk about phase in relation to waves, what we mean is that the particles are vibrating in the same direction and at the same level of displacement. However, phases of particles near each other, on a progressive waves are different. While you expect particles to vibrate in such a way that they are in phase, in the same direction, at the same level of displacement, for progressive waves, you are going to discover that the phases are going to differ. And for that reason, we conclude that actually stationary waves are different from progressive waves. Therefore, when you make a stationary wave, you cannot claim that the wave is stationary unless you have two waves of the same quality, same characteristics, and you superimpose them on each other so that now one is the negative of the other. Or we could say that one is actually a mirror reflection of each other, forming series of nodes, and these are points of zero displacement. Then we have maximum displacement at antinodes. Now, one of the most important applications of this phenomenon is when we are playing musical instrument, a concept we are going to learn in our next lesson, where we shall find out how we are able to produce sounds by way of generating stationary waves. Thank you.